Hello students, in today's class I'll discuss one of the important property of coordinate compound, bonding in coordinate compound. Bonding in coordinate compound. As the name implies, coordinate means in this case central metal atom form coordinate bond with the ligands. See, think of a salt, it is a simple salt. In this case, cations, anions are held together by Na plus is a cation, Cl minus is an anion. These two ions are held together by electrostatic force of attraction. Electrostatic force of attraction. In this case, Na plus cation is an S block element, but there are some elements which are known as the D block element, which are placed between S and P block element. D block element, due to D block element, there is special characteristics which is not possible by S block element. Na plus will never form coordinate compound, but D block elements such as iron, cobalt, nickel, all of them will be capable of forming coordinate compound. D block element, what is the special property? Number one, small size. Small size. Number two, high charge. Availability of incompletely filled d subshell. Most important part, you filled d subshell help them to form coordinate compound. When I will discuss bonding in coordinate compound, there are two concepts. Bonding in coordinate compound, I don't go too fast because it is totally concept based. One is VB theory, one is CFT. As the name implies, it means valence bond theory. It is called crystal field theory. Both have some merit as well as some demerit also, but first I will discuss their merit. VB theory has large merit, so it is in force, still it is have application. Many of the property of coordinate compound can be explained on the basis of their VB theory. Let us discuss. Think of a compound such as, let us start with a compound. Think of a compound K4FeCN6. In this case, F is a central atom. It is a D block element because Fe atomic number 26. So electronic configuration of Fe will be argon 4s2 3d6. In coordinate compound, central metal atom, Fe is a central metal atom. Central metal atom has two kind of valency. One is primary valency, which arises due to loss of electron from valence shell. Like ionic substance, it also has a tendency to lose electron. After losing electron, the incompletely filled d subshell present together mix up together to form hybrid orbital. The hybrid orbital form coordinate bond with the ligand which is represent within third bracket. In this case, Cn is the ligand which is capable of forming coordinate bond with Fe after it loses electron. Achha, I will explain all this part to you. Depending upon the number of coordinate bond, the central metal atom undergo two kind of hybridization. Number of coordinate bond made by the ligand to the central atom are of two kinds. First of all, precondition, central metal atom loses electron to form cation. The empty d orbital present after loss of electron from the central metal atom mixed up together to form hybrid orbital. The hybrid orbital form coordinate bond with the ligand. Okay, let us discuss this. In this case, K4FeCN6 as the case we have taken out. Cn, which link to the central metal atom, is called ligand. As the number of ligand is 6, so when the number of coordinate bond is 6, it has two kind of hybridization. One is D2sp3, which is called inner orbital octahedral complex. Or sp3d2, which is known as outer orbital octahedral complex. Shape of the molecule is octahedral. Suppose it is the central metal atom. In this case, 4 ligand will be in the plane. L1, L2, L3, L4 are in the plane, 1 above the plane, L5 above the plane, and L6 below the plane. The shape of the molecule will be octahedral. In case of coordination number 6, when it will form inner orbital octahedral complex and when it will form outer orbital octahedral complex, this thing I will explain in detail to you. Just go on, let us explain in case of coordination number 6 when the outer orbital octahedral complex, when inner orbital octahedral complex is possible. I have taken the case of K4FeCN6. We can take the other cases also. In this case, Fe is a central metal atom. Atomic number of Fe was 26. It is argon 4s2 3d6. In this case, what is the charge of Fe in the compound? Total charge of the compound will be 0. 4 potassium should have a charge of 4 plus. Suppose let the charge of Fe be x and each Cn is -1, it will be -6. So x is equal to 2. So in K4FeCN6, charge of Fe is 2, which is possible by loss of 2 electrons from the valence shell. Fe has outermost electronic configuration as it is a d block element. Outermost valence shell will be outermost s subshell and penultimate d subshell. But loss of electron first from the s subshell, then remaining from d subshell. In this case, as Fe loses 2 electron to form Fe2 plus, 4s subshell contain 2 electron. So in this case, Fe loses 2 electron forming Fe2 plus. After forming Fe2 plus, it has no electron in the s subshell but d subshell containing 6 electron. D has 5 orbital where I have to accommodate 6 electron. Then 6. Now main things comes. When it will form inner orbital, when it will form outer orbital, how should I judge it? Remember, case 1, when d subshell contain 1 to 3 electron, now with Fe, the ions and molecules which link to the central metal atom in the coordination sphere The part which is written in the third bracket is the coordination sphere. The ions or molecule linked to the central metal atom is called ligand. Ligand are of two kinds. One of them is called strong field ligand. Other is called weak field ligand. How should I know whether a ligand is strong field and weak field? There is a way, I will tell you, don't worry. First of all, case 1, when the d subshell containing 1 to 3 electron, whatever be the nature of the ligand, inner, strong or weak, that doesn't matter, always it form inner orbital octahedral complex. So what I told you, now when d subshell contain 1 to 3 electron, always it form inner orbital octahedral complex. In doing it, I have to take 2 electrons from n-1 d subshell, 1 electron from next s subshell, and 3 electron from p subshell. Suppose if the valence shell is 4s, then in this case for inner orbital octahedral complex, it will be 3d2. When the valence shell is 4s, in this case it will be 3d2. D subshell should have principal quantum number 1 less than s and p. 3d2, 4s1, 4p3, called inner orbital octahedral complex. On the contrary, when d subshell has same quantum number that of s and p, it is known as outer orbital octahedral complex. So if it is ns1, np3, nd2, it is known as outer orbital octahedral complex. Now we know D has 5 orbital, 3 orbital are in between plane, that is dxy, dyz and dzx. Other two, dx square minus y square and dz square, are along axis. Okay, it is in dxy, dyz, dzx are in between axis. On the other hand, dx square minus y square and dz square are along axis. dx square minus y square has 2 lobes. 4 lobes, sorry, along x and y axis. It is dx square minus y square. And dz square only has 2 lobes along z axis. In case of octahedral complex, we should take 2 orbitals which are along axis. That is, we should take dx square minus y square and dz square. This is very, very important. Keep in mind, whether inner or orbital, that doesn't matter. The 2 d orbital takes part in hybridization must be dx square minus y square and dz square for octahedral complex. Now, as I told you, ligands are classified into 2 categories, strong field ligand and weak field ligand. How should you know which is strong field, which is weak field? When the donor atom are halide donor atom, then oxygen donor atom, then nitrogen donor atom, then carbon donor atom. In this way, strength of the ligand increases. So the ligand which we usually come across are as follows: I minus, Br minus, strength of the ligand, Cl minus, F minus, then OH minus, then H2O, then C2O4, then NH3, then Cn, then CO. CO is the strongest ligand. Okay, so when the linkage is through halide, it is the weakest ligand. Linkage through carbon, it is the strongest ligand. Now, think of the case Cr H2O6 3 plus, this is first case, and Cr CN6 3 minus. In both the cases, charge of chromium is 3 because H2 is a neutral molecule, its charge is 3. In this case, Cn has a charge of -1. So x minus 6 is equal to -3, makes the charge of chromium is 3 only. Chromium having outermost electronic configuration argon 4s1 3d5. So Cr3 plus will be what? 3d3. What I told you, when the d subshell containing 1 to 3 electron in Cr3 plus, we are getting 3 electron. H2 is a weak field ligand, Cn is minus is a strong field ligand, but both the cases it will form only inner orbital octahedral complex, because after loss of 3 electron, we have 3 electron left in d subshell. Now what happened? In this case, Cr3 plus is this. This 2d subshell is empty, so from 3d I should take this 2 subshell. From 4s it will be 1, from 4p it will be 3. All of them are empty. So 2 from 3d, 1 from 4s and 3 from 4p mixed up together to form 6 equivalent d2sp3 hybrid orbital. So it is an example of inner orbital octahedral complex. Whether you take H2O or Cn, that doesn't matter. It will form only inner orbital octahedral complex. After the complex is formed, d subshell containing 3 unpaired electron, hence it will be paramagnetic. Magnetic moment of the compound will be what? Magnetic moment is denoted by mu is equal to root over of n into n plus 2, as n possesses 3 unpaired electron. So the magnetic moment will be root over 3 into 5 is equal to root 15 Bn. Okay, now let us take the case of this case. Fe Cn6 3 minus, Fe Cl6 3 minus. In this case, charge of Fe is 3. In this case also charge of Fe is 3. But according to the list I have provided, Cn is a strong field ligand. Cl is a weak field ligand. In this case, Fe has atomic number that I already told you. After loss of 3 electron from Fe, it become argon 3d5. That is Fe3 plus. Now let's proceed. Fe3 plus equals to 3d5. Now we have 4s empty, 4p empty, 4d empty. In first cases, what is Fe Cn6 3 minus. Cn is a strong field ligand. Under the influence of strong field ligand, what happened? Two electrons from d subshell paired themselves. Though it is against Hund's rule of maximum multiplicity, still it happened. We know that so long as vacant orbital available, no pairing takes place. But in this case, under the influence of Cn minus, which is a strong field ligand, pairing takes place. So what happened? The 5 electrons should be accommodated in 3 d subshells, that is dxy, dyz and dzx, and make 3 d orbital empty. These 3 d orbital empty, which it is dx minus y square and dz square. Then 4s is empty, 4p is empty. All of them mixed up together to form d2sp3. In this case, all of them will be capable of making from 6 coordinate bond with 6 Cn minus. As the bonds are directed in space, so coordinate bond compound has definite geometry. As I told you, that is the case of octahedral. So out of 6 Cn minus, 4 will be in the plane, 1 above the plane, 1 below the plane, and after the compound is formed, it has 1 unpaired electron, hence it will be paramagnetic. Magnetic moment corresponds to 1 unpaired electron, that is 1 into 2, n into n plus 2, 1 into n plus 2, n is 1 plus 2 is 3, root 3 bn. But when I take the case of FeCl6 3 minus, what happens? Cl minus is a weak field ligand. Cl minus will incapable of pairing electron present in d subshell of Fe3 plus. In this case, 6 orbital which will take part in hybridization will be 1 from 4s, 3 from 4p, 2 from 4d. Which 2 d orbital from 4d you should take? One is dxs minus y square and dz square. So in this case, Fe Cl6 3 minus, it is the case of your sp3 d2 hybridization. D subshell has 5 unpaired electron. Cl minus will incapable of pairing electron present in D subshell. 3d5. So we have 4s from 1, 4p from 3 orbital, 4d from 2 orbital. All of them are mixed up together to form sp3 d2 hybrid orbital. After forming the hybrid orbital, D subshell contain now 5 unpaired electron, contrary to the earlier one where it has just 1 unpaired electron. Hence it will be paramagnetic due to 5 unpaired electron. Magnetic moment will be root over of n into n plus 2, n is 5, 5 into 7, so root 35 bm. So by measuring the magnetic moment, we are in a position to say which of them form outer orbital, which of them form inner orbital octahedral complex. Now, last part, when D subshell contain 7 to 10 electron in D subshell, irrespective of nature of ligand, it forms outer orbital octahedral complex. Octahedral complex only. Think of the case Zn NH3 whole 6 2 plus. NH3 is a strong field ligand. Or take the case of this Zn H2O whole 6 2 plus. It is a strong field ligand. It is weak field ligand. Now zinc has charge of zinc in both the cases is 2 only. Zinc having atomic number 30, electronic configuration argon 4s2 3d10. After loss of 2 electron from d subshell, electronic configuration of Zn2 plus become argon 3d10. This subshell is completely filled. So we have to take whatever be the nature of the ligand, it doesn't matter. It has to take 1 from s orbital, 3 from p orbital and 2 d orbital which are along axis to form sp3d2 outer orbital octahedral complex. After forming coordinate compound, this zinc doesn't possess any unpaired electron in d subshell, hence the compound will be diamagnetic. Magnetic moment in this case will be 0. Earlier case it was the paramagnetic due to presence of unpaired electron which will be attracted by magnetic field, but it is the case of diamagnetic having no unpaired electron in d subshell, hence in both the cases it will be the case of diamagnetic only. So this is the case of coordination number 6. In case of coordination number 4, there are 2 kinds of hybridization. For coordinate number 4, that means 4 coordinate bond made by the ligand to the central metal atom. There are 2 kinds of hybridization. What is? One of them is called DsP2. As I told you, bonds are directed in space, hence they have definite geometry. It is called square planar. It is called square planar. Another, it can be sp3, that is called tetrahedral. Generally, I've used the word generally but not always. Generally, strong field ligand form square planar complex. The d orbital this used for hybridization will be dz square. Dz square with 1s and 2p mixed up together to form dsp2 or square planar. The d subshell which should be taken in hybridization should have principal quantum number 1 less than s and p. That is n-1 dz square, then ns1 np2. It's called square planar. On the contrary, when I take one orbital from one orbital from s and 3 orbital from p, it forms sp3 or tetrahedral. Let us discuss one by one the case of coordinate number 4. Think of the case NiCl4 2 minus or NiCN4 2 minus. In both the cases, charge of nickel is 2. Nickel having outermost electronic configuration argon 4s2 3d8. After loss of 2 electron, which account for the charge of nickel is 2, Ni2 plus having outermost electronic configuration argon 3d8. Now that 3 d orbital, 8 electron in the d orbital can be represented this way. Eight 3d8, 4s is empty, 4p is empty. Now when one electron moves over here, Then we have 3d 8, 4 orbital accommodate this 8 electron, one empty d orbital mixes with 1s and 2p forming dsp2, a square planar. One 3d, one 4s, two 4p mixed up together form 4 dsp2 hybrid orbital which form coordinate bond with Cl minus. As there is no unpaired electron in d subshell, hence NiCl4 2 minus or tetrachloronickel 2 ion will be diamagnetic. Magnetic moment will be 0 as it possesses no unpaired electron. On the contrary, in the case of NiCN4 2 minus, Cn is a strong field ligand. So NiCl4 2 minus, Cl is a weak field ligand, Cn is a strong field ligand. Under the influence of Cn minus, pairing of electron in d subshell takes place to make one 3d z square orbital empty. Hence NiCN4 2 minus will be the case of dsp p2 hybridization, square planar. But when I consider the case of NiCl4 2 minus, as Cl is a weak field ligand, Cl will incapable of pairing electron in d subshell. Hence in this case what happened? NiCN4 2 minus will be square planar dsp2 hybridization with no unpaired electron in d subshell. Now I'll discuss the case of NiCl4 2 minus. In NiCl4 2 minus, as Cl minus is weak field ligand, hence no pairing of electron in d subshell takes place, so 8 electron will remains as (3d8). 2 electron is unpaired, 1 from 4s, 3 from 4p, mixed up together to form 4 sp3 hybrid orbital. All of them forming coordinate bond with 4 Cl minus. It possesses 2 unpaired electron, hence NiCl4 2 minus will be paramagnetic due to the presence of 2 unpaired electron. Mu will be is equal to root over of n into n plus 2, that 2 into 4, that is root 8 Bn. Hence it will be paramagnetic. Now I told you generally weak field ligand from tetrahedral complex, strong field ligand, square planar complex. But think of the case of this. NiCO4 tetracarbonyl nickel 0. CO is a neutral molecule, so Ni should have a charge of 0. Now in this case, Ni has electronic configuration argon 4s2 3d8. Is it so? Now in this complex, as nickel doesn't having charge 0, so CO is the strongest ligand. I told you under the influence of CO what happened? 2 electron from 4s moves to 3d. So in this case what should have under the influence of CO? It has nickel 3d10, which is quite unlikely, but it happened to make 4s orbital empty. 4s 0. Now we have 4s and 4p. 1 from 4s, 3 from 4p mixed up together from 4sp3 hybrid orbital. All these hybrid orbitals form coordinate bond with CO. As in this case it possesses no unpaired electron, hence magnetic moment will be 0, mu will be 0. Though CO is a strong field ligand, still though CO is a strong field ligand, still NiCO4 is tetrahedral. Shape of the molecule will be tetrahedral. Complex will be tetrahedral, and magnetic moment mu is equal to 0. In this way I try to explain the VB part of coordinate compound. It is more or less I've discussed all the part. Still, if you have any problem, you can contact me on my WhatsApp number, which is given in the description box. Hope you will find it good, and try to subscribe it to your friends and your known person and make the channel grow. Later on I'll come with more such video.